Here x is what we call a three-adic number. It's the number 2 plus 3 plus 9 plus 27 plus every single power of 3. So notice that it's 1 plus 1 plus 3 plus 9, so the geometric series in powers of 3. And of course, if this was treated as a real number, that infinite series diverges, so this would just be infinite. But this number is to be considered as a formal power series. It's just a number that we're going to define some addition and multiplication on that kind of numbers and forms what we call the ring of three-adic numbers. There are several ways to express three-adic numbers. That's one. Another one would be to write it in base 3 so that the coefficients are 2, 1, 1, 1. So it would be 2 and then infinitely many ones afterwards. So the question here is, what is x? What happens if I multiply x by 2? 2 times x will be 4 plus 2 times 3 plus 2 times 9 plus ... plus 2 times 3 to the n. Now, in base 3, that is not allowed, so I have to do a carryover. I'm going to write 4 as 1 plus 3, and here's 1, and there is one more 3, so 2 times 3 plus 3, that would be 3 times 3. But now this is not allowed, I have to do some carryover. So that 9 comes over here, 2 times 9 plus 9, that's 3 times 9, but that is 27, so that is not allowed, it would carry over. So the 27 that was here, now there is the 2 times 27 became a 3 times 27, but that is 81, so it carries over. So that becomes another 0, that's 3 times 81, but that is 3 to the 5, so it carries over, and so on and so forth. And every single term becomes the 0 except that 1. So 2 times x is 1, and therefore x is 1/2. Now, you might be a little bit disturbed by that disappearance of all these terms. Let me write this number in another format that is the way I usually write my three-adic numbers. Instead, I like to write my three-adic numbers as an infinite sequence of congruence classes. The first coefficient is the value of x modulo 3, the value modulo 9, the value modulo 27, and so forth. So this term here would be the value modulo 3 to the n. And I prefer to write three-adic numbers in this format because now addition and multiplication of three-adic numbers is just component-wise. So if you have two three-adic numbers, you would just add their first coordinate and their second coordinate and their third coordinate and so on. And if you were going to multiply, you just would multiply their first coordinates, and that would be the new first coordinate. The product of the two second coordinates would be the second coordinate of the product, and so on. So it makes addition and multiplication very easy to work with, while the expression as an infinite series is very difficult to work with when you actually want to do arithmetic of three-adic numbers. Now, let's see the expression of x modulo 3 to the n, which is this number here, is given here, and if I simplify that using the geometric series formula, then I see that the expression for x modulo 3 to the n is actually 1/2 plus 3 to the n divided by 2. But this term 3 to the n divided by 2, modulo 3 to the n is 0. 2 is invertible modulo 3 to the n, so it's a unit. This is just 0, so x modulo 3 to the n is just 1/2. So that expression is actually x is equal to 1/2, 1/2, 1/2, 1/2, 1/2, all halves. So x is equal to 1/2.